OK, so today I'll be presenting assertion-based repair of complex data structure. This is part of my thesis work at the University of Texas at Austin. So let's start. So, and as an introduction, so data structure corruptions are bugs that reduce the reliability of programs. Now, programmers always use assertions to check the validity of a program. Now, what happens if if we have a violation of an assertion? Traditional approach is terminate the program, debug it again, and run it again. However, this approach, although it's used, sometimes it even doesn't work, because suppose you have a file system with corrupted data. Again, you will have the same violation every time and every time. So even if you debug it, re-execute it, if you have persistent data, you might fail again. So I'm going to propose present a new approach for handling these violations. And this approach is repair. So instead of an assertion checking for the validity of the state of the program, how about an assertion checks the validity, and if the program has something wrong in its state, it repairs it. And how do we do that? So the new approach for handling this violation is repair the structure, the underneath the program state, continue the execution, and report that violation that's there. Now, how to repair these structures, we will see soon. A brief background, what are these complex structures that we are talking about? So most of the programs use complex data structures, for example, red-black trees, intentional naming networks, or software caches. These structures have special constraints. For example, a red-black tree, all the paths should have the same number of black nodes. In an intentional naming system, a naming network, you should not have any cycles. In a software cache, you should have correct hash table, and you should have the correct doubly linked list to keep track of which is the least recently used item in the cache. So these complex properties are the ones that are going to be violated, and they might corrupt the program. Any violation of any of these properties might corrupt these programs. Now, what differentiates one structure from the other? Well, these are called the structural integrity constraints. And these can be grouped into two parts. The first part is the structural characteristics. For example, you can say a linked list is acyclic, or a doubly linked list should be circular. So this is all about the structure. The second part, which differentiates them, is the data characteristics. And for example, in a red-black tree or in a tree, the values of the items inside the tree should be ordered. Now, how do we check for these characteristics? Using assertions. Now, these assertions can be written, or the description of these characteristics can be written in declarative language. For example, there are lots of languages like Alloy, Z, ASML. These languages are something that use first-order logic. Or they can be written using an imperative language. And by imperative language, you mean the language that we use for our coding, for example, Java, C# or whatever we are using. Now, how do we describe these characteristics using Java? We have a method that returns a Boolean, and it simply traverses the graph of the heap and checks for all these characteristics. Now, for example, for a binary tree of 8 nodes, so given a binary tree that has a root and a size and the left and the right element for each node, a method repOK, which returns a Boolean, simply checks for each of these characteristics. For example, if the root is null, the size should be 0. Anytime you hit a visited node, then you should return false. Anytime you hit a visited node while traversing the right branch, you should return false. Or if the number of elements inside the tree is not equal to the size value of the tree, you should return false. Now, repair performs the following. It takes this repOK description and it traverses it to see if you have an underlying tree. And if not, it will mutate the tree to repair it to become a valid binary tree. So what does repair mean? So given a structure or any program state such that, and the class invariant repOK that describes what is the underlying state, if we have not s.repOK, which means if there's a violation in the program, the repair will mutate s and will generate s prime such that s prime.repOK returns true. Now, is this the intended behavior of the program? No. But it is a state where the program can continue and might not crash because of a corruption inside the data structure. So for example, if we have such corrupt structure, so the size, we have a corruption in the size, we have a corruption in the right field over there and 2 here, repair will take this structure and generate that one over there. However, it might not only generate this one. There's another possibility, because who said that this node here is the corruption? Because maybe this is the corruption, and you can generate another 3 that is valid, but it's not the same one that the program intended to generate. So what are we repairing? We repair faults in the structure, and we repair faults in the data. So in the previous example, we had faults in the size member, and we have faults in the structure. So we have two things to repair, and 2 things might get violated during a program execution, which is the structure of the underlying heap and the data that's found inside. So to repair the data, we use an approach called symbolic execution. And symbolic execution, I'll give an example about symbolic execution soon. And for structural integrity constraints, we used a systematic search, which has been used for test generation. I'll also describe it soon. So symbolic execution. What is symbolic execution? Symbolic execution is a technique that runs the program on symbolic values and not concrete values. This thing has been like since the 70s, and it's been used for testing purposes because it traverses all the paths of the program and generate a condition that says to go into this path, you should have these conditions on the input. If you want to go to another path, you have another conditions in the input. For example, so let's take this simple program. If a concrete execution with x equal 1 and y equal 0 will first check is 1 greater than 0, we'll take the if statement, execute x, and execute y, find x again, check that, yep, it's -1 is not greater than 0, and terminate. Whereas symbolic execution does not consider values. It considers x and y as symbols. And it will start by x equal big X, y is equal big Y, and check. If x is greater than y, we should go this way. If x is less than y, we should go to the other path. And as it continues executing, it just updates the symbols. So if we see here that it either goes this way and ends, or goes that way and executes all the statements, when it hits another if statement, it will either go to the left or to the right. At the end, it will generate 3 path conditions in this case. If x is less than or equal to y, it terminates. If x is greater than y, however, the difference is less than or equal to 0, it will end with, it will assert false. And the third condition will terminate successfully. Why do we need these? So if a program terminates because of a corruption in a data value, and the repo K should return false. So symbolic execution will give us the condition so that repo K does not return false. Once repo K does not return false, we can generate the correct data values that will allow the program to continue. A systematic search. Now, to repair a structure S, we first execute repo K. We need to see if maybe the structure is OK. So repo K will tell us if the structure is fine or the structure is faulty. We execute repo K, and we monitor how are we accessing the fields. Once repo K returns false, then most probably a field is corrupt, and we need to repair it. Now, how do we repair this field? We look at the last field that we visited, and we modify it. How are you going to modify it? We modify it, and we re-execute repo K until repo K returns true. Now, how do we modify these fields? If the field is a data field, we change it into a symbolic value. And we say, OK, this field was 5, for example, and we had a corruption in the structure. And we just note that, OK, this field should not be 5. If we have a reference field access, we non-deterministically mutate this field to, we first test the field to null and see what happens. Look at everything that we saw during the traversal of repo K and see what happened. And we choose only one new node. And only one new node is the trick here, because you don't have to visit everything in the structure. You only need to see one non-visited node, and that's sufficient to check all the isomorphic structures that you can see. So let's take an example of the binary tree again. So let's look at this binary tree. We first execute repo K on this one. So first of all, we visit the root node. Then we visit n0, n0.left. We visit n1. And once we visit right, we notice that, oops, we visited n1 earlier. So there is a corruption in the structure. We note that, hey, we visited root, and then we looked at left, and then we looked at right. And we trigger our repair program. What does the repair program do? It will backtrack on the last field that we saw, which is the right node. And what's the first choice to do? Since the right field is a reference field, it's not a data field, the first choice to do is set it to null. It sets the field to null, and we have this structure. Cool. It continues and re-executes repo-k. Now, when we re-execute repo-k again, the structure looks fine because it will check root. OK, root is fine. Left is fine. We don't have any right node anymore. So everything is fine. It hits the data corruption. Oh, the size is 2. The size is 0. However, the number of elements that I visited till now is 2. So what do we do in this case? Change this thing into a symbolic value and add the condition that will make repo-k return true. So what's the condition? The condition here is size does not equal 2. So the path condition is not size does not equal 2. You send it to an integer constraint solver. And in this case, it's very easy to return size equal 2 and modify it in the structure. And we re-execute repo-k again on this one. And there you go. The program will succeed. Another example, a doubly linked list. Now, suppose we have this doubly linked list with a corruption in node n3. Now, what do we do in this case? n3, the node coming out of the next field coming out of n3 is corrupt, and it's a reference field. So the first thing to do is we try null, and it fails. Try n1. We don't always remember, we have to try everything that we visited earlier because we might find a solution early on without trying a new field. Try n2, didn't fail, didn't succeed. Try n3, didn't succeed. Try n4, and the structure is repaired. So if we keep following this approach is complete, i.e., it will find a structure for you if such a structure exists. However, if you notice that this is all controlled by the way you write this repo-k method. So if this repo-k method is unsatisfiable from the beginning, so if the repo-k method simply returns false, then that's it. You cannot do anything. You cannot repair the structure. So we make the assumption that the user provides repo-k, which describes what the underlying structure in the program means. So speaking about that, how did we perform our experiments? Well, we generated a set of valid structure of different subjects, and I'll show you the subject soon. And we broke all the structures by injecting faults that break all the integrity constraints. For example, in doubly linked list, we break the circularity constraint. We make next does not equal to previous. We make next point somewhere else. And then we trigger our repair routine and run the program. That's the first experiment. The second experiment is we used a software cache. And in this software, we ran a faulty software cache. And we ran the system on like a system that uses caches. We simulated the microprocessor. And every time we had a fault in the program, a null pointer exception was being thrown. If we didn't have our repair routine, this thing will crash. So with our repair routine, it will repair itself, and the program continued. However, it provided a log that, OK, there is a problem in your program, but it successfully continued this time. Check it out and fix it. So instead of crashing, you repair. So the performance of this approach is as follows. We tried it on a bunch of data structures. And if you notice, we can handle structures with hundreds of thousands of nodes with like almost 20 faults within 10 seconds. And even like complex structures, for example, a file system in 15 seconds, an intentional naming system in 9 seconds. So the performance is pretty good. However, if more faults exist in the structure, then the performance might grow quadratically, not linearly, as we see here. But we expect always that once we have bugs in the structure, the program is once you assert that and check that the program is fine, you will be able to catch this bug earlier on. So that's why we expect lower number of faults than like between 0 to 20 faults to appear in a program that's in a buggy program before either crashing or triggering our repair routines. So how hard is it to write these assertions? Now, the repair idea is not new, and it's been there since the 60s, or like once they started the computers. So once you have an application, and if you need to increase the reliability of the application, you write a specific routine that repairs this application. For example, FS check disk, which like checks file system. So once you have a tree in the file system, before terminating the computer, you run this tree over the file system, and you fix your file system. So these were there. But what's the difference between our approach and the approach that was there? Older approach always use specific routines to repair the structure. So to use repair, you need to inspect all the bugs that might occur in the structure, and then write a repair routine. However, in our approach, we don't have any code specific for repair routine. We only have the description of the structure, which most probably will be there because this is the spec. So there are lots of other languages, for example, other languages like JML, which you can describe your repo in the same way, which can describe what are you doing in the structure in the same way. So most programs have these repo methods in them, or have some method to check the validity of the program. So in this way, it comes for free. Another point is like, for example, in a so the properties of a program are known while implementing the program. So it's easy to write a repo. However, efficient repair routines are not. So you have to see what bugs can occur in the program and how to repair them. So in this way, writing an assertion is pretty easy. Like, we wrote assertions for more than 15 benchmarks. And basically, writing an assertion is a simple checking of the properties. Each one took around like 15 minutes or 20 minutes to write an assertion for the program. Now, how efficient can repair be? So we looked at the problem of generating one. Repair is basically the problem of moving from the structure that you have to generate another structure that satisfies the conditions. So there have been other tools for generating large data structures. For example, Korat and Testera are two tools for generating data structures from such descriptions. So you give them the descriptions, they generate all the data structures that you want. These tools proved efficient for small structures. And since we are only generating one, and we expect the fault to be in the neighborhood, so we expect the distance between a faulty structure and a non-faulty structure to be very close, then our repair routine, that's why our repair routine was able to handle 130,000 structures with 130,000 nodes in less than like 10 seconds. Applications of repair. Now, we looked also at how to apply this. So repair is fine. It can repair the structures and let the machine continue. Now, what are different applications for repair? One is generating a large data structure. So since we know how to repair data structures, but however, we don't know how to generate them given just the description. Like, give me a data structure that's acyclic and the nodes are ordered. Well, we can easily generate a random graph, which we don't care what is this data structure, and run this repo on it. Every time it will return false, it will repair, keep repairing it until it generates something new. And this idea was also like published or will be published in August. So that's another use of repair. Another way which was investigated by a colleague of mine, which is repairing the program. So if I know that this program, this doubly linked list is always failing because the next field is not equal to the previous field, then most probably the underlying program has the same property. And how about translating these repair actions that we do into actual Java statements and plug them into the program? So automatically generating the fix. Now, how good is this? We've tried it for simple data structure. We haven't looked at very complex data structures for this one because it's tricky. How do we know that a next field is not equal to the previous or the previous is not equal to next? Which one to assign? So it's very hard to know how to generate the Java code to repair, like how to generate a fix for a bug automatically by looking at the violation. But the idea is there, so we're still investigating it. So related work, as I told you earlier, that fault tolerance and error recovery are featured in software systems long time ago. First, most of the past programs use these specialized routines. So FSCK or the IBM MVS operating system, the Lucent 5ESS switch, which is a phone switch, also continuously use these routines. Every time, that's why it never breaks, because every time it breaks, it repairs itself and continues. Recent work in 2003 was by Dembski and Reinhardt, which are at MIT. And what they did is, instead of using Java like we did, for example, using the replicate and execute this replicate and check when will it return false, and when it returns false, repair the program. What they did is translate the program into another language. So they have a compiler that takes the program, which is written in C or C++, and translate it into another language, analyze that language, repair the structure over there, and send it back to the program. So it generates the repair routines that are similar to those that are there. So given a program, you feed it the program, it will say, OK, this program might fail here, here, and there, and these are the routines if it fails. So these guys, I think they won Best Paper Award. And the academic community liked this idea very much. So that was, again, a motivation that since they do it in declarative language, it's easy to do it in an imperative language, because usually the programmer is writing Java and not any other new language to model the system. So conclusion, what we have here is a new view of assertions. So you usually say, if you say assert rep OK, right now you check the validity of the program. However, if we say assert rep OK using our framework, it will check the program, and if it fails, you repair the program. So now we have a way to repair the program. Similarly, the same approach, the same algorithm can be used to generate data structures. So we can generate data structures to test our program, and we can inject this framework inside to repair the program in case anything missed the testing. And the biggest conclusion is assert first programming. And always write assertions to describe what you are writing in the code. And like all the academic tools that are there use these descriptions to generate tests for these structures. So once we know what's this code doing, in any way, any language, not necessarily, we use imperative languages. Any declarative languages like JML can be used to generate unit tests automatically. So most of the test automation, test generation is easily performed if we have a way to know what do you intend. What's the difference between the pre-state and the post-state when you call this method? Or what do you expect the data structure always to be? So we expect the heap always to be in a tree-like. Once we have this information, we can easily repair the structure, and we can have more reliable systems. Now, comments on implementation of the structure, like how do we implement repair? I don't have this in the slide, but I'll describe it because I thought I'll be short in time. So how do we implement this repair? So given the Java program is translated into bytecode. So we take the bytecode, and every time the program accesses a field or a data value, we change this access into a method that we provide. So instead of f.next or n0.next, we say n0.getRepairNext, which is a special method that we provide, which keeps track of what fields did we try till now, and it can mutate the fields to apply the algorithm that I just described. So once you see a violation, we already keep track of everything that happened in the system. We can easily mutate the field to all the previous stuff that we did, or to a new thing that we expect to happen. And any questions? OK.
How would this be used is this typically used in conjunction or to the exclusion of test-driven development?
OK. So this, as you noticed, we don't need any implementation. So OK, let's start by the applications of this thing. So the last slide, I talked about the application of this repair thing, which is to generate larger data structures. So there, if you need to generate larger data structure, which is somehow similar to test-driven developments, where you generate your test inputs before even writing the implementation, and you don't even need any implementation to do that. However, for repair, you also don't need any implementation to do that, but still the source of the bugs is from the implementation. So if you need to use it for test generation, this is perfectly for test-driven development. And if you need to use it just to repair your program, you need the program to repair it, right? So it is like highly related to that thing, and that's how we motivated the other approach. Like we just need the declaration of the structure, and we need this repo-k method, and there you go. We can start generating tests automatically.
Okay, so this again relates to the applications of this. You said that your repairing was non-deterministic, right?
Yeah.
So, I mean, aren't you scared that this could lead to programs that will repair themselves 99 out of 100 times perfectly, but then 1 out of 100 times?
Exactly. That's very like that's.
So if I'm writing code for a Mars rover, 99 times on Earth it's going to work, and then when it actually goes to Mars,
okay. So this brings us to 2 points. So first point is completeness of the algorithm that's repairing. Okay. So maybe this like Mars rover will not crash for like this 99 times on Earth, but like it will crash this one time, and the repair routine is complete. I.e., if it can be repaired, it will repair it. So if there's a bug in repo-k itself, the repair routine will not repair it. Now, a more tricky thing that this approach is like should handle carefully is data. Like, although we use symbolic execution, but I can't take a binary tree which has the values 5, 10, 20, and which are in a different order, and repair them by putting values 1, 2, 3. So we don't want to lose the data. We need to reorder the data. And that's where we face the problems, where we need to have some way from the user to tell us that, OK, do not change this data. Just try to reorder them. And once this is given, we can do that. But for the completeness of repair, if repo-k is written correctly, the program will be repaired. At least the data structure underneath will be repaired.
But then, don't you risk introducing I know your program won't crash, but don't you risk introducing logical errors? Because
OK, so but think of it this way. So the program expects a valid structure. So for example, assume like you have a delete method. So the delete method expects a binary tree with some values, and its output is a binary tree, but missing one of the values that you wanted to delete. So what we're doing, if initially we didn't have a binary tree, we reordered the values and we reordered the structure to be a binary tree and apply the delete. So what we're doing, we're not changing anything with the logic. We're changing the structure because you are expecting a binary tree, but you are not expecting a specific shape. So we are changing it. However, if we change data there, that will be like a problematic because you're expecting some value to be there, but it's not there. And however, sometimes if the data itself is corrupted, we can do nothing. Like we cannot generate any new data. We can isolate the data, but we cannot do anything for it. Cool. Yeah.
If you're missing data or the data is corrupted, then you might just end up with like the trivial case, right?
Sorry?
If you're missing data or the data is corrupted, you might.
Yeah, you will end up with a trivial case. So yeah.
It also kind of depends a lot on how well the repo case is written, right? You want like the more important assertions to come first, right?
Exactly.
If there's an assertion like no list must be 3 or something like that,
so
then that can't be repaired. Are you going to like generate a node to make sure that?
Yeah, you can do that. So
just add like some random.
Yeah, so that's the thing. So we can take another example which we faced, which is suppose there's something happened with the reachability of the structure. So you started with a linked list of 1,000 nodes, and the corruption happened at node 9,000, and the rest of them are garbage collected. So you can't get these nodes anymore. You can't get the data. How to repair this? You cannot. But what we do is cut the linked list with the number of nodes that we have. So it is still a linked list with the values inside it and continue. Or we have a configuration which says add random nodes with this default value. But like you cannot just guess what's the next one. Now we are planning on extending it, okay, predicting what's the next value from the older values, but this like doesn't meet our goal, which is trying to repair the program rather than predicting what can go there.
Okay. Yeah. You also said that you intercepted every method call.
Sorry? We intercepted every field access. Let's just one second.
So you should know exactly,
okay, so in this example, we need to know what is the last field that we accessed so that we start triggering it.
Okay.
And maybe the problem is not in the last field. Maybe the problem is in the field before that.
Right.
So we have to try everything for the last field. Didn't work, go to the previous one, change it, and go back to the last field and try it again.
Just to record what fields you touch, right?
What field you touched, yeah, because most probably the violation in the structure is because something that you tried earlier, or something that's gonna appear in the future, and that's why we also try one single visited node.
But how often do you check rev OK? Only when like
Okay, now, that depends on how, okay. So this is a program, okay, let me say, I will send you again the paper which we discussed this issue very much, like, and we have experiments on how, if we call it with every garbage collection, if the program is most probably is not gonna crash, and you check it with every garbage collection, then you have a higher overhead than if you're checking it once you call a specific method that you expect this method might be buggy, or like somewhere in the program, some part of the program that you need to be very highly reliable. That's where you assert. But anywhere, like you need to know when to assert, right? So the repair routine triggers when you call assert rep OK. But when to call assert, you can have a conservative approach, which you need the system to be highly reliable. So you check it with every garbage collection. In our experiment, we checked it on every time we throw an exception. The system throws an exception. We check it. And if we can find the fault from there, we catch the exception and continue. Cool. Somewhere over here. Someone had a question? More questions? I think he had a question, but he's working. Fine. OK. So that's it.